I'm going to go through a few sets of slides very quickly based on talks I gave on the Associahedra in Los Angeles in 2018 in February. In my thesis in 2007, I explained how the Associahedra polytopes in particular were the appropriate mathematical setting for scattering amplitudes in particle physics. Now, the full blown quantum field theory will involve more than just Associahedra polytopes, but it was over 10 years before the community appreciated the importance of these structures within category theory. Now, an operad is a sequence which you count 1, 2, 3, 4, 5, and so on. A sequence, in this case, of polytopes, which I've drawn in pink. And the definition of the polytopes is combinatorial, and here we show how the vertices are defined by trees, which are binary, they have a root, and they're within the plane. The pink edge is known as an associator. The pentagon is an important axiom in what we call symmetric nodal categories, and that is the basis for quantum mechanics today. Each of these pink polytopes is indexed now on the bottom there by a green tree with one level. That stands for the interior of the polytope in whatever dimension we're in. So here, the dimension of a space, we're not talking about vector spaces, but the idea is the same. The dimension of the space replaces the cardinality of a set because we're doing quantum logic for quantum field theory. The number of vertices here, 1, 2, 5, 14, is the Catalan number. Now, just focusing on the pentagon, we see that it's not only the vertices, but it's also the edges that are defined by trees, and all we have to do is collapse one interior edge to draw the tree along an edge. So the trees are not necessarily binary, they have a variable number of leaves coming off each vertex, and we've accounted for pretty well all the trees here on 4 leaves, which have a root. Let's move on to the three-dimensional associahedron, which is very important for us. Here we've drawn the simplest path in dark blue from the source vertex to the target vertex. And that's an easy way to start labeling the 14 vertices here with trees, now with 5 leaves. So of course the number of leaves is going up by 1 in each dimension. Every edge is once again a flip of some small piece within a tree which looks like the single associated edge that we started with. So every edge in every dimension is of this type. Here in dimension 3 we have not only pentagons from dimension 2 but now square faces as well. There are many alternative definitions for the same Catalan numbers. Here we have Young diagrams, which I've coloured in with pink and yellow to show you how we count up both vertices and faces by colouring in Young diagrams which are rectangular in shape. So looking at the top 2 rows where we have 6 little boxes in a diagram, there are 8 diagrams with pink boxes, but only 5 if we discount the yellow diagrams. These associahedra will now appear in what we call simplices, but everything is discrete here. There are no continua, and we're going to start with just edges with points along them, which we can think of as being jeweled trees. We're going to do the same thing as we go up in dimension, so from edges to triangles, and then from triangles to tetrahedra, and so on. And what we're going to do is we're going to place polytopes with inside the discrete simplices, which I've drawn here and labelled with coordinates, x and y for an edge, x, y, and z for a triangle, and so on as we go up in dimension. On the top right here we have the famous tetractys diagram with its 10 points, and if I look at the way I've labelled the points, everything is commutative. It doesn't matter what order I put the letters in the word. But the non-commutative words are paths on the cube, where the simplex is a diagonal slice of the cube. And this happens no matter what simplex we draw. And here we have the pentagon appearing naturally inside the tetractys. So there are really 3 pentagons that we can bury inside the tetractys, the way I've drawn it there with a little green pentagon, although it's not geometrized correctly there. And on the left we've taken the 3 coordinates and set x to 1 to obtain natural coordinates on the 5 vertices of the pentagon. Similarly, the all-important associahedron in dimension 3 will appear inside a tetrahedron, and this time there will be 4 corners because there are 4 points on the tetrahedron, so there will be 4 copies of that 3-dimensional associahedron. Now the coordinates have changed. What we're saying is that if we have x, that's 4, 0, 0, 0, because there are 4 copies of x and no copies of the other coordinates. In other words, the natural integer coordinates for these discretized simplices come from the letters. If we wanted to geometrize the detritus by shifting edges by natural angles, we get the same kind of angles that we need to define components of the pentagon tiling in the plane due to Roger Penrose. This tiling is very important for us, as shown by Battaglia and Prato, because it comes from the 8-dimensional integers. In other words, I can fill the complex plane densely with a set of numbers that really come only from 8-dimensional integers. Now, once we have our Associahedra polytopes, they compose. So, for example, there's a Cartesian product of the topological space, which allows us to compose any 2 Associahedra. Now, we will represent those compositions again by trees. There are different kinds of trees all over the place in this theory. And that's what an operator is. It's a set of things which have a nice composition, which we are representing here by trees. So let's take the simplest example. I take 2 edges and I compose them to obtain a square. That's a square face on that 3-dimensional pink polytope. And here in red I've drawn the trees there that show you how we're composing those 2 edges. Now, as you can see, I can't draw any higher dimensional examples because we've already run out of dimensions to draw things in, but the idea is the same. The trees are representing that composition in topological spaces. Now, quantum field theory in the 20th century is all about normalization. Don't worry too much about what that is. From our perspective, normalization is governed by the Kohn-Kreimer-Hopf algebra, which is really all about trees. Now, not the kind of trees we started with, another kind of tree, but we can think of this as like an operator composition that we were doing on the Associahedra. All of this is really about scalar field theories because the underlying classical mathematics is all about real numbers. So here I've drawn CP1, so the Riemann sphere with 3 marked points. This is a moduli space, and all these moduli spaces are tiled by Associahedra polytopes when you look carefully at how you compactify the spaces to make them nice classical spaces. Now, this is studied in many contexts in both mathematics and in mathematical physics. But it's very important to understand that historically we were looking at this, I was looking at this within a category theory framework, trying to apply category theory directly to the foundational axioms for quantum field theory, and it really had nothing to do with string theory. However, there were some beautiful papers, in particular by Witten, about twistor geometry, where he was looking at these kind of surfaces and thinking of them in the context of string theory. But everything I do is really about the foundational axioms. Now here we're going back to the basics of projective geometry again, and I'm going to take these 3 points here, which is really a triangle cover of the circle in cohomology, and I'm just going to cut the triangle so that it's like a long extended line, and I'm going to turn it into RP1 by turning it into not a triangle but a pentagon. So the rule is I add 2 points near infinity and the point at infinity instead of just the point at infinity. And here I'm dualizing my original cohomology diagram and I get the pentagon. Now that might just look like an arbitrary trick to say, oh look, RP1 is really a pentagon, but the nice thing about this is that the idea carries on to dimension 3. We do the same thing again. We take the cohomology in grey for RP2, which looks like this. And now I'm going to dualize it and draw a green diagram. But instead of adding 2 points, at the ends of the edge before we get to infinity. Now what we're going to do is we're going to add 3 more points, so we're going to end up with 14 green points in total for that 3-dimensional associahedron. Okay, it's coming up now. So 3 extra points for the plane on the outside, and a point at infinity which I have not drawn gives you the right faces with 6 pentagons for that 3-dimensional associahedron. Now it doesn't really matter what happens in higher dimensions. It's the low dimensions that are difficult to understand. Dimension 2, dimension 3, dimension 4. And in higher dimensions, the associahedra can all be obtained from the ones in low dimensions. Now let's look at another important polytope sequence. This is the permutahedra sequence, where the vertices are permutations on however many objects we have. Here in dimension 3, I need 4 objects to draw 24 vertices, which are the 24 elements of the permutation group on 4 objects. On the bottom left, we see that these polytopes tile 3 dimensions, and that works in every dimension. These polytopes are closely related to the associahedra. Here I have the associahedron on the right, and if I chop up all the faces into triangles and number them using a simple combinatorial rule called parking function, then those 24 little triangles can be dualized to become the 24 points of the permutahedron. Once again, this works in every dimension. It's very easy to define the rule for mapping one polytope to the other and vice versa. And our third special sequence of polytopes is the humble cube. Here we have a map from the permutahedron in dimension 3 to the 3 cube, which sends a permutation to its sign. So some permutations get sent to the same signs, so that 24 vertices go down to 8. It's very simple. For example, 1, 2, 3, 4 is mapped to plus, plus, plus because we went up each time we stated a new number. Now the divided cubes, if I allow arbitrary divisions on cubes, can be mapped to the discrete simplices that we were using. Here I've drawn a hexagon slicing through a cube where I have 3 points along each edge on the cube. And what we want to do, this is what we call motivic mathematics. What we want to do is we want to take all these sets of polytopes and all the relations between them and build a higher dimensional abstract structure which gives us the cohomology we need to describe physics. Here's an example of a polytope which combines an associahedron and a permutahedron to give 120 vertices. That's 24 times 5. So we've put a little pentagon at each vertex on that 3-dimensional permutahedron. There is such a permutoassociahedron in every dimension, and I have a better picture of it here from a nice talk given by Michael Buchanan. And this structure, with a combination of associahedra and permutahedra, is 2-dimensional from an axiomatic perspective, meaning that we replace those 1-level index trees that we started with right at the beginning with 2-level trees, so that some trees represent associahedra, some trees represent permutahedra, and in general the trees represent both polytopes. Here we have all possible kinds of index tree in a table by Byers and Dolan, which underlies homotopy. So these are fundamental structures for algebraic topology and other branches of mathematics, which we know are crucial to the axioms for quantum field theory in this modern framework. And there are a large class of other polytopes that we might consider, but the ones that we've looked at so far already have a lot to do with physics. So in summary, so far, we are seeing that the one-dimensional structures are not enough to capture the physics we need. Here on the bottom left, for example, we have 3 colouring on the associahedron. We want to look at knots and ribbons because we know those are important axioms. In fact, even to get a symmetric noidal category for quantum mechanics, you need the axiom of a braiding. And it turns out that the braidings come up an awful lot in quantum computation and other branches of physics. The philosophy is to look at the computations in the Standard Model and in quantum gravity beyond the Standard Model, in particularly for neutrinos, without starting with classical space-time, momentum variables, and a whole lot of real and complex geometry that we don't understand from an axiomatic point of view. Since things are never observed to infinite precision, we don't need all the complex numbers. Motivic numbers are good enough. And I'll leave you momentarily with the Kia, the endangered species Nestor notabilis. And now I'm going to move on to part 2, which was the second talk I gave on the Associahedra. This one is a little bit more technical for those who don't care much about mathematics, but it's a follow-on from what we've said last time. Let's look again at this image of the green associahedron dual to the standard cohomology for RP2. And remind you that there's a fundamental connection between projective geometry itself and these associahedra polytopes. They're not merely tiles for moduli spaces, which is how they're usually used. There is also a connection to Lie algebras, for example, but we won't go into that at all today. Let's start by looking at the axioms for Hopf algebras. Remember, we briefly mentioned that last time in the context of renormalization. Here we have a categorical axiom for Hopf algebra, and at the bottom there, I've turned the blue trees into non-commuting forest trees with fewer nodes. That's a simple combinatorial trick that you can do. And on the right, you can see how those brown trees correspond to our coordinates, which we had coming from discrete simplices. So now I'll summarize quickly what I'm going to go through here. I'm going to start with Francis Brown's calculation using the Associahedra of nice integrals for physics. Then look at some relations in Hopf algebras, go back to the affine coordinates within our discrete simplices, then say a few things about motives and a few comments on braids and their connection with the Associahedra. Now, the simplest calculation we can do, following Francis Brown, is zeta 2. So zeta is the Riemann zeta function, and we're looking at values of the Riemann zeta function for integer arguments. Here we have its proper definition in terms of integrals, and we look at various coordinates. Here we have cubical coordinates and simplex coordinates. The T1 and the T2 for the simplex is drawn here around the blue triangle, and we have two special points which need to be chopped off to create a pentagon. If you look back up at the integral on the top left, those two special points are not well defined there. That's why we need to truncate and create the pentagon. And as you might have guessed, now when we go up, we're going to get higher dimensional associahedra for other values of the Riemann zeta function. The rule is to fix the points 0, 1 and infinity on the Riemann sphere, and that's why we have only two coordinates for 5 particles in this case. Here we have some further coordinates called chord coordinates, which are defined here naturally in terms of the simplex coordinates. These chord coordinates are associated to cross ratios here in terms of complex variables. So we can see, if we look at the associahedra and their index trees, or rather the polygons dual to the trees, we can see quite clearly what the connection is to complex geometry. Zeta values obey many interesting relations, and these are well understood as relations for Hopf algebra. In this case, a Hopf algebra of zeta values and generalized multiple zeta values, all with integer arguments. So looking at that example, zeta 3, 1, here is the integral definition, and we're only using either z or 1 minus z there on the denominator. That allows us to encode that object in words, in letters, and here is an example of a relation using a product of zeta 2 and zeta 2, which is the simplest one we can write down. A Hopf algebra has both products and a unit for product, and also coproducts. And a coproduct comes with a co-unit. So it has those 4 elements to make a bialgebra, and the addition of something called an antipode will make it a full-blown Hopf algebra. Now let me remind you again of our coordinates on discrete simplices. Here we have the pentagon again with the affinized coordinates, starting from the black word coordinates on the detractors tile, and the alternative numerical coordinates, which are the natural integer coordinates for arbitrary discrete simplices in any dimension. So there are integer coordinates for cubes and for associahedra embedded inside simplices, which are diagonal slices on cubes, and there are natural integer coordinates for permutations for the permutahedra polytopes. Like Stephen Hawking, was it Stephen Hawking? I'm not sure, but somebody said that God invented the integers and men invented everything else, which means they messed everything else up. Because really all we need to do everything is the integers. Now, of course, we need to add a great deal more structure to get nice algebras and to fit them together to match the geometry that we're getting out of our axioms automatically. I'll finish off here with the well-known connection between the trefoil knot and the associahedron, which is not well understood until now, really. Here, zeta 3 is connected historically with the trefoil braid there in B2, and it's also connected using Brown's approach to this three-dimensional associahedron. So we have our 3 special series of polytopes, the permutahedra, the associahedra, and the cubes, all connected by these maps that I've been describing, which are canonical maps. We have, for example, a Hopf algebra called Solomon's Hopf algebra on the vertices of cubes. We have Hopf algebra for every permutation group, which is just the group algebra for the permutation group. And we would like to combine these structures into a higher dimensional structure for quantum field theory. This is what we mean by saying universal cohomology or motivic cohomology. The coordinates for the geometry itself, and the algebras we build associated to these geometries, these are all canonical in an axiomatic framework for higher dimensional category theory. So the higher dimensional category theory, if we do it the right way, is basically telling us how quantum logic operates. And as observers, what we're doing when we decide to measure something is we're doing quantum logic. We're setting out some statement within quantum logic and determining what it is that we're measuring and making the measurement. That's it for today, so thank you everybody for listening.